Good evening all. Welcome to the last session for this particular course. So as discussed in last week, we will first get started with a review of two journal papers, and then we will go to how multigrade is implemented. I think my screen is visible now. Yeah, thank you. So we'll go through. This is one recent paper where they have used the simple algorithm that we discussed in the sessions to essentially understand how this radon is a radioactive element, is distributed inside a typical room. You have your typical room has walls, windows, and all these substances will naturally have some radon. So their objective is to understand how is this radon distributed inside. How is this radon is distributed inside the room. So just to give you a quick schematic, so this is your room and this is a human person inside. So the idea is to get the distribution of radon inside the room. So as always, first you get started with your governing equations. So you have assumed so this is your continuity equation followed by your momentum equation. In the momentum equation, so we have some source terms. So instead of the mu that we were usually doing, since it is a turbulence, is a turbulent regime, they use an effective, your viscosity will kind of have terms both from the laminar part, that is a normal dynamic viscosity. Something happened to the page. Yeah. So you have your laminar viscosity as well as your turbulent viscosity. So everything is very similar. So this is your diffusion component, this is the pressure component, and this is your other source terms. The source terms essentially here are the terms that will add to your radon distributions. Like radon is being continuously generated, so from walls, windows, or whatever other sources are there, you will be adding those terms into the source term. So when you discretize this using your simple algorithm, so this will be in your SC and SC term, and this will go into your diffusion terms. In addition to this equation, you also need to consider your transport equation. So this is your convective diffusion equation. If you just rearrange this part to the LHS side, so you can see that this is very similar to your general form of general scalar transport equation. So this is your unsteady term, this is your advection term, this is your diffusion term, this is your SC, and then this lambda is your SP. So this is very similar to whatever we have studied in this session. Next step is once you set up your boundary condition, once you set up your governing equations, you need to come up with some boundary conditions. So here we have our variables are my velocity and the concentration of radon. So these are velocity and your concentration are the variables that I need to find. So my boundary conditions will be expressed in terms of velocity and concentrations. And from there, maybe like people are joining, we'll wait a couple of minutes so that it will get stabilized. So all these equations are all very similar to whatever we have discussed in the class. So you have your continuity, then you have your momentum equations like x, y, z, and then you have your scalar transport equation. In our class we discussed essentially about temperature, but then you can have other concentrations. So in this particular paper they are considering the distribution of some particular species. Say in this case it is a radon gas. How is this distributed inside the room? and then your boundary conditions are specified. So the wave velocities are specified at the inlet. So if you recall the schematic, so you have to specify your out of this, you have your boundaries on the, this is the doors, you have one inlet and this is your outlet, and then all other walls will be you have to specify the velocity on all other walls. And for concentration, to solve the concentration equation, you also need to specify concentration on all the walls initial, and then you also, since it is an unsteady problem, you also need to give the initial concentration and initial velocity distribution throughout the room. If you are already familiar with it, this is how you actually feed in the information from real experimental data into your numerical simulation. So for the velocity, for suppose they are using some kind of volume flow rate, average volume flow rate, and then they incorporate into this effective area term and then put it as in boundary condition. And similarly for all other parameters, they have come up with some experimental values. They have taken from some other experiments and then use those values as your boundary conditions. And as far as the solving method is concerned, that is exactly similar to whatever we have discussed in the session. So use a simple algorithm. These are the list of boundary conditions. They haven't specified exactly what the parameters are. We'll go to another paper where they actually specify what are the several things, like you have to specify your under relaxation parameters for your pressure correction equations, and then you also need to specify what are your even for your momentum equation. We will see them maybe in the next example. So this is clear. So the method that we are discussing in class is something that is actually being implemented. This is a very recent paper, so it should be like once you get familiar with this process, you should be able to do it on yourself as well. We'll just show another one. A slightly different domain. Here we do not have any heat sources as such. This is say this is your room and you have an inlet duct that carries the cool air, and then this is an outlet from where the hot air escapes from the room. So this is the domain that is being considered here. Even here the problem is like straightforward. So you have to specify your inlet conditions and then outlet conditions, and then all the walls you need to specify your velocities, and then you have to use your simple. So that is straightforward. So how do you start solving it? The governing equations are again straightforward. The first step is always you start with your governing equations, continuity equation, and then your RANS equations. In this particular case they have used RANS. You can also use some of other models if you are familiar with. So the point I want to highlight here is how do you actually, there are several parameters that you need to set up before solving them. We do not know them before actually solving. You need to, it's a kind of a trial and error kind of, so you start with some value and then you see if it is converging. If not, then you change these values. The values, they are essentially you have an under relaxation factor.
Hello.
Yeah.
Sir, actually what is the difference between SST K omega model and K epsilon model? How can we choose the K epsilon model and K omega?
It actually differs from application to application. I cannot actually comment directly on which one is suitable for your application or not. So you should actually try out different models and see if it works or not, because all of them are just an this is a kind of modeling, right? In modeling it's different from what you actually observe. So you are eliminating a lot of factors and then you are making these models. So you do not know which one of them might work beforehand. Only after you try it you can say that one of these is working better than the other. So people have tried out all these methods for in this particular problem. Say this particular problem is pertaining to do air distribution inside rooms. So for this they have tried these models and have found out that these models are in good agreement with experiments. Before actually knowing the problem, I cannot comment it. That's the same with even the model is one, and the same with your relaxation factors. You cannot say beforehand which one will work for you or not. You have to run the simulation for various of these and then you will have to see which one is working for you. But the common steps are straightforward. So once you have set up your model, and then you have to do the mesh independent study. So mesh independent study is where you see that even on refining your mesh, you do not actually get any significant change in your end results. And then what are the values that you report? So when you say once you have done with your simulation, what are the values that you will be reporting? that depends on case to case. So in this particular scenario, their objective is to understand how the temperature is, how this flow is distributed from the horizon. So this is my inlet. So from here, how is my flow getting distributed as it goes away from the inlet? They want to understand that. So depending on that, they will see when by refining the mesh if those particular velocity values are changing or not. And once you are done with your mesh independence, then you try various parameters for the whatever your converged mesh is, and then you see that is a parametric study where you can vary the inlet location and all other parameters, and then see how your end result is actually varying with that. Even in the previous work, which I have not shown, so what are the values that you report after doing the simulation is essentially one is the mesh convergence, and then you try to see if all of these are physical or not. So if any of these can, you have once like just because your model is giving you these values doesn't mean these are the actual values that happen in reality. You also always need to validate it with some experiments, say scale or full scale experiments, full scale or small scale models. So the ones they are trying to plot here is how is concentration distributed inside the room for various cases. Say in this case they are varying the ACH is essentially it's kind of a ventilation rate. So air changes basically tells you in 1 hour how much fraction of air within the room is getting replaced with the new fresh air. So it's 0.3 per hour, 1 per hour, and 2 per hour. This is a very high ventilation rate. So we can see the concentration is more or less distributed. So this is all cases when doors and windows are open. Now we can see when one of them is closed. Yeah.
Sir, actually I have a little bit doubt to find the Nusselt number in the access fluent. Sir, whenever I can ask.
So basically you are facing trouble with the software, or is the value not matching with the other values? Like what kind of problem is that?
Sir, if you give me permission, can I share a screen for only for 2 minutes? And I want to discuss this one.
Okay.
Yes. Sir, can I share this one?
Yeah.
Okay, thank you so much.
Yeah, your screen is visible. You are actually on mute.
Hello.
Yeah.
Yeah, sir, screen visible?
Yes, yes.
Sir, actually in this I consider a pipe.
Can you
Diameter
zoom?
0.2 meter and length is 3 meter.
Okay.
And inlet temperature 293 and velocity inlet 0.05 meter per second.
Hmm.
So that Reynolds number equal to 995.2143.
Okay.
And this is a constant heat flux condition
Hmm.
for fully developed flow. So that value of Nusselt number equal to 4.36.
Constant. Okay.
Sir, how to calculate this value in ANSYS fluent?
So you already simulated, you already done the simulation in ANSYS, right? Like it's already completed.
I done the simulation. And meshing also perform in fluent meshing such that orthogonal quality is greater than 0.1 and skewness less than 0.1.
So then there is an option where you can actually get this expression. So okay, you already, can you open can you open the simulation, or it will take time or something?
Sir, I can.
Or maybe we will take it at the end of the session.
Okay.
So basically your problem is like mesh is converged, but you do not know how to exactly get Nusselt number from the data. That's it, right?
Yeah, I actually it's a value, it's a truth, na? If for fully developed flow, the value of Nusselt number equal to 4.36.
On the wall, yes.
Or for constant heat flux.
Hmm.
I want to validate this result.
So you calculated you were able to calculate the temperature distribution inside the pipe, right?
Yeah, temperature outlet actually according to
No,
conservation
not the
of
outlet. On the wall.
on the wall it's very
Yeah, but were you able to get the temperature distribution on the wall?
heat and mass transfer, if given that value of Nusselt number 4.36, it's a constant.
Yeah,
So
but
that I
how do
want
you
to
calculate your
this-
Nusselt number?
Yeah. Nusselt number and temperature profile on wall.
Yeah. What I'm trying to ask is basically you need Nusselt number. So to get Nusselt number, how do you approach it? You need to essentially Nusselt number is Hd by K. You know the K, thermal conductivity of the fluid. You need to know the heat transfer coefficient, right?
Okay.
Now how do you get your heat transfer coefficient? You know the outlet bound, like you know the boundary condition that your heat flux is Q. So Q equal to H times delta T, where delta T is the temperature of the wall minus some reference temperature, say inlet temperature or some reference temperature. Your heat transfer coefficient.
Reference, actually, one is the surface temperature at a particular location corresponding to bulk mean temperature of a fluid at a particular cross section.
Yes.
So that the difference is calculated local Nusselt number. Na? I want to this graph at the end of this paper and the value. So whenever you will see, then I will discuss with you.
Okay, we'll get back to this end of the session if time permits. So we'll quickly go through the paper and then we'll have to go through multigrade. After that, we'll come back to this.
Okay, thank you so much.
Yeah, you can stop sharing your screen.
Yes, there is.
Yeah. So coming back to where we were. So you can see these results where you have your door open and the concentration is very less, and when the door is closed, the concentration gets it kinds of get concentrated near these corners and other areas. So these are some results as kind of your sanity checks, just to see that the simulation results are physical. Because if you find some of these to be non-physical, then you need to essentially change your governing equations in a way to incorporate the actual physical effects into this. So say for example you forgot to add the source term in your governing equation, and then you just take the normal momentum equation, then you might not find the results to be physical. Then you need to add your source term, which essentially takes care of this additional radon that is coming from, say, humans or walls or some. These are essentially source terms which will increase the concentration of radon in addition to your normal momentum equation where it is coming because of advection terms. So these are some physical things that you have to check, or maybe the sanity checks you might call them. The remaining ones are you just check the temperature distribution and velocity, species distribution, and then the next one is your velocity distributions. So the post processing is quite straightforward. Now that you have many softwares, you will be able to do it. Now coming back to multigrid. So in the last week we discussed that the last session we will mainly focus on multigrid. So I'm not sure if you're already familiar with multigrid. Is there anyone who is already familiar with it, or maybe I can assume that you are not familiar with it and we have to start from the beginning? No, I'll assume the second one. Not familiar. Okay. So when we are discussing, say, Gauss-Seidel method, the final equation is very simple. So you have some set of equations written in the form Ax equal to b, and you are trying to solve it using some iterative algorithm. So the problem here is how many iterations does it take? Sometimes it can converge pretty fast, sometimes it might take time. So why do you think it is taking time for some scenarios and not for others? Say suppose you have done some k iterations. After k iterations you have some function x, just to put k is essentially just to say that xk is not the actual solution, but then this is the solution you are obtaining after performing k iterations. So essentially x is my final solution, or the actual solution, x minus xk is my error. So this error, if you are familiar with your Fourier series kind of, so can actually be written as some function of your so if it is a one dimensional say suppose, then you can write it as some expansion of sines and cosines. I am just writing sines, but you can it can be expressed in terms of function of sines and cosines. So you will have several periods. So what happens is when you are doing Gauss Seidel, what it essentially does is you have some equation, some AP phi p is sigma a and b times phi and b plus b. Say suppose we don't have any source term, so you just have this equation. So say suppose you have a 1D problem, a very simple one. So this is your phi 0 and phi 1 on the boundaries, and somewhere in between you have discretized, and your equations will go as phi I for ith cell will be, say you have the equation is something like d square phi dx square equal to 0. So you don't have source term and your diffusion coefficient is 1. So your discrete equation will be 2 phi I is phi I plus 1 plus phi I minus 1. But you can see this phi I plus 1 can essentially again be written as half of, for phi I plus 1, phi east will be phi I plus 2, and then you have west is phi I. Similarly for phi I minus 1, you will be having the east cell is phi I and west cell is I minus 2. So we have phi I plus 2 and phi I minus 2, and again phi I plus 2. See the essentially the I plus 1 has a coefficient of 1 by 2 here, and again phi I plus 2 can be written in terms of east and west, and this phi I plus 1 again can be written in terms of the previous one. So if any time you are essentially taking only the coefficients from the east and west cells, so the information is only coming from the nearby cells. For any ultimately what happens is the ith cell will get information from I plus 1 and I minus 1, which in turn will again get information from the previous ones, and it goes on till you reach your boundaries, where at the boundary this information will propagate here, and this keeps on coming here till it reaches your ith cell. So information has to propagate from the boundaries to your current cell. So if you have a very high number of cells, so we have very good resolution, that essentially means your n or number of cells is too high, then it might take a little time for that information to propagate from the boundaries to your current cell. So this is one factor, and the second factor you need to consider is okay, it can be expressed in a slightly different way. So say suppose like I have said, so if I take an initial guess of something like since any error function can be expressed as some combination of your sine and cosine functions, I will assume some function like this, where you have some, where I is essentially the ith cell in my 1D grid. So if I assume this as my initial guess, and my problem is d square phi by dx square equal to 0. So what do you expect? The solution is straightforward. So if suppose phi of x equal to 0 is 0 and this is my problem, the solution is phi equal to 0 everywhere. So if I give this as my initial guess and see how actually Gauss Seidel performs, like how the values of phi change with iteration number, what is observed, or maybe I can quickly show you. So this is my problem, like just I have told. So I've just taken the ideal solution is phi of x equal to 0 everywhere. But then if I give an initial guess something like this, sin of k pi x, and see how Gauss-Seidel will change as with iteration number. So I've considered a grid with the size of say 64, and your k is essentially the frequency of your error. So your error term can have several components. So you can have high frequency components and low frequency components. So that frequency is essentially this k. Dx is your grid size delta x, and then your remaining everything is straightforward. So I've just defined the coefficients. Your AP is A east plus A west, and then updated the boundary values to be 0. The Gauss-Seidel implementation is also straightforward. Now if you see what happens when I change the k value, so this is for k equal to 1. So this is at iteration 0. So the blue one is at 0 iteration, so initial guess. And then after performing 50 iterations, you can see the value has not changed too much. Ideally Gauss-Seidel should converge, but then it is taking a lot time, more time. So maybe it converges after even more a number of iterations. So I've stopped at 50 iterations. Now if I change the frequency to 2, in that particular case, it kind of damped a little faster than what happened in the first case. So here if you can see the difference between the maximum versus the difference between the maximum here. So the damping is quite fast. So even in, for the same number of iterations, if the frequency is increased, the relative error is kind of decreasing. So if you increase the frequency even further, so for this is for a frequency of 4, for k equal to 4. So you can see it kind of damped it very fast. So for 50 iterations, it is kind of almost close to our actual solution of 0. So if I increase it further to k equal to 8, then after 50 iterations, the solution is already kind of converged. So what is happening here is when you have very high frequency, Gauss-Seidel is actually damping those errors. So when your all the high frequency errors will be damped by the Gauss-Seidel method, they will be damped by even the low frequency ones will be damped, but it will take a lot more number of iterations to damp these low frequency ones. So this is exactly the problem that will be addressed by multigrid. So you have both your high frequency and low frequency components. The low frequency components are essentially the ones that happen over large distances. So that is essentially why we are calling them low frequency. So you have your x changing from 0 to 1, and for one change to be detected. But in the previous case, so just at 0.5 you have these changes. So when you have very fine mesh, your Gauss-Seidel method was not able to have that long term or basically as you are refining your mesh more, your Gauss-Seidel is becoming short-sighted. It will only know the nearby values, and that's essentially why it is able to damp the high frequencies much better than your low frequencies. So how do you solve this? So the idea is, say you perform just k iterations. So you have axk, your original problem is ax equal to b, but then you stop after k iterations, and then axk will not be ax, it won't be equal to b, but then you will have some error. So that error, if I write in this particular way, it can be like if I subtract this from this, you'll be getting b minus axk. This is my error term. So if I can somehow get ek, error at k term, so after performing k iterations, I will add the error term to xk, and then I will be able to get my original solution. So, but the problem again here is how will I solve this particular equation? So if I solve this equation again using the same Gauss-Seidel method, then I will again come to the same problem. So it won't be able to solve because the errors are the low frequency errors will again be not able to, Gauss-Seidel will not be able to capture these low frequency errors. So what we have to do is to use a coarser mesh. So why is Gauss-Seidel not able to see the low frequency ones is because you have lot of changes. So when you have more number of cells, any change here will take more time to get noticed here. If this is my ith cell, any changes here will have to go through all these cells to come back to here. If I use a coarser mesh, something like this. Any change here will be immediately like in one iteration the update will come to this particular cell, but here you might have to go through a more number of iterations. So but the problem with this coarser mesh is if you use a coarser mesh, sometimes it might give you non-physical results. So like previously we have seen even you have in convection diffusion cases as well. So your delta x, there is some, even in case of an unsteady problems, you know, like delta t and delta x are related. So for a given delta t, you cannot arbitrarily take any delta x. So because of these limitations, there will always be some limitation on how coarse you can go and get a mesh for. So you should not be actually solving for this original equation. Instead, the idea proposed in multigrid is somehow you find some mapping between this and this. So instead of solving the original equation, you will solve some other different set of equation that will give you some idea about how the error should be updated in the finer mesh. So this is my finer mesh and this is my coarser mesh. I'll solve some set of equations, we'll come to what set of equations a little later, and then somehow get an estimate for the error term in the finer mesh. I won't be solving the error term directly in the finer mesh because I know Gauss setup will not give me the result. So I will solve for the error on the coarser mesh and use some mapping between coarser and finer mesh to update the error in the finer one. Is this clear? I think the idea should be clear. If the idea is clear, then we can go ahead and actually see how it is actually implemented.
So what you mean is as we iterate, we change the grid. Is that right?
Not really. So you do not change your grid. So your problem will be solved on the original grid. Now you are making a different problem and solving it on a coarser grid, such that this different problem will give you some information on how to improve your solution on the original grid. So you won't be actually solving the problem on a coarser grid, like the original problem on the coarser grid. You will solve a different problem. And then regarding the
I'm sorry, I lost you there a little bit. My earphone fell off. Could you repeat that last, please?
So basically you have some original problem and then you formulate a different problem and solve it on a coarser mesh, and this coarser mesh should give you some idea on how to improve your accuracy on the original mesh without actually solving the original problem. As far as iterations are concerned, so we stop after a certain number of iterations. It's not like we change iteration or something. We solve a different problem after that. So say suppose originally your Gauss seidel has to do 100 iterations. So what we do here is we stop after 50 iterations and then solve the problem on a different grid and use that to update the value after 50 iterations.
Okay.
So how we do it, we'll see a little later. Is that answer your question or something else?
Not entirely, but maybe I'm missing something. It's okay.
Yeah, maybe after we go through the entire one, it might be clear.
Yeah.
Yeah, so we will go through the idea then. So the idea is, so you have different levels of mesh. Say L is basically the level of mesh I am saying. So you have the L equal to 0 is your finest mesh, the one on which your problem is actually being solved for. And then you have several other levels. So just for now we'll consider just two layers, L equal to 0 and L equal to 1. So this is your coarser mesh. So here your original problem is being solved. So you have some set of equations. So I'm just calling A0, X0 equals B0. And then on the next level you will be solving a different problem. You have A1. So I'm just using E instead of X because here you will be essentially using this E1 to update this X0. So what I am trying to say now is, now instead of actually solving for X0, I'll stop after a certain number of iterations, say after k iterations. Then I won't be getting B0, instead I'll get something else. So let's call that, if I solve for this, so X0 is the original solution, but I stopped after k iterations. So x0 minus x0k will be my E0. Now what I do, I calculate my residual. After k iterations, is essentially what I should be actually getting is B0. Instead what I have got is A0 times x0k. So what I do, use this residual in the next level as B1. So this residual will go into my B1 and then I will solve for E1. So how I get A1 is, we will come to that. So if I solve this equation, then I will get E1, and from this E1 I will update my original x0. So x0k plus you use this E1 somehow, this should be or closer to x0.
Closer to the x0 that you want, right?
Yes, that is the actual solution. Yeah. So there are two different ways in which this, like now the only question that remains is what are this A1, what is this B1? Like A0, B0 is we know because we have our original problem. What are this A1 and B1? That's the question that remains to be answered. So there are two ways in which these are calculated. One is your geometric multigrid and then the algebraic multigrid. Geometric is a straightforward one. So you have, say, some mesh like this. So this is my L equal to 0, the finest one. So what I do for the coarser level construction is I'll just merge some of these cells and create the new ones. So say suppose 0, 1, 2 and 3. I'll merge these two cells and make one new cell. And I'll merge 2 and 3 to get another cell here. This is algebraic multigrid. So what I'm essentially doing here, so
Boundary conditions and all,
everything remains the same. So instead of, so how do you get these values here? So previously you were having AP0, AP1, like AP A and B terms we were having previously. Now you have to update the values accordingly in these new cells. Like in the new discretization, you need to get the new values of AP A and B, and then you have to solve for this equation. It's like you get A and B and then you will get E1 from there. We will actually maybe do one example, but the, to do that, the one difference that exists is here you get the residual term for a R0. R0 is essentially of dimension say 4 by 1, but in the next cell when you are solving for B1, like I have written B1 is essentially R0, but R0 is a matrix of dimension 4 by 1. To choose K, so which K were you referring to? Okay, how many iterations I have to do in the first step? Okay, so all of these are kind of a hyperparameter, so we cannot actually comment before how many you have to take. Depends, changes from problem to problem. We cannot finalize on 1K at least.
So we will do trial and error and choose 1K.
Yes. Yeah, so so your R0 is essentially of dimension. You have four cells in the first level, so you will have 4 residuals. But for the second one, your B should have only 2 of them. So I need some mapping between this 4 by 1 matrix to a 2 by 1 matrix. So some mapping between this. So this is called the restriction operator. The one that goes very simple is you just add the residuals of these two to calculate the residual here. You add these two to add here. So essentially you have R0 plus R1. Maybe let's not confuse with the notation. So I'll use 0 for the cell, subscript for the cell index and superscript for the level. So R0 plus R1 will essentially go into my first level 0 cell. And similarly, R2 and R3 will go into my second cell in first level. So now you know the B values. You know A1 is calculated from your AP A and B terms once you discretize your equations for this particular grid. then you need to solve for a1 e1 equals b1. You know b1 and a1, so you'll get e1, but again e1 will be of dimension 2 by 1, but I need to update my x in the finer mesh, so which will be of 4 by 1, so I need some another operator here to actually do this mapping, so this is called prolongation operator. The straightforward way to do it is just take the error, so whatever error is there in 0 cell, you just use the same ones in 0 and 1, whatever is there in 1 you just use the same in 2 and 3, so whatever is trying. So for the first cell on first level I'll consider 0, so from this I'll update my x for the first cell on first level after k plus equal to, so okay, if you are already familiar with that notation, or maybe you can use the whatever value you got after k iterations plus this error term a01. Similarly, I'll update my first cell on 0 level to be whatever is there previously after k iterations plus the mapping is we'll just use the 0 cell, because for during the first restriction stage we use the same residual, so we'll update that. So you have E01. Now for the remaining two cells, so x2 and x3 on first level, we take their previous values and update them with the second residual, so second error, so E1 on the first level, E1 on the first level. So this is straightforward. So now you know the second cell, you solve the errors and then you use them to update your previous values, and now you have your x updated on your finer mesh. So this seems simple. The only problem you can see right here is you have to discretize on your coastal mesh and then you have to get your equations again.
And you have to run iterations again, right, on L equal to 1?
Yeah, but you have less number of cells, so it will be faster than what you would have done on the original one, right? Yes.
Converge, right?
Yes, to some point. You have to perform some number of iterations even on L equal to 1. Or if you take even more number of, say, L equal to 2, 3, 4 and so on, you need to perform more number of iterations on each one of them. The advantage you are getting here is if you are using L equal to 0, you know that it will take more number of iterations because you have some high frequency errors that won't be damped out easily by Gauss-Seidel method. This is because of your problem with your Gauss-Seidel method. If you are using some direct method, then you might not have to worry about it at all.
So, if I understand correctly, let's say L equal to 0, let's say in theory it takes say 100 iterations, and so let's say we stop at 50. So L1 is guaranteed to be less than 50, right?
Yes.
I mean,
Yes, theoretically.
Right, theoretically. So totally you get like say 70, let's say 20, let's say L equal to 1.
Something lesser than 100.
Yeah, less than 50, correct?
Only for L1 it should be less than 50, only for L1, okay.
Yeah, L1. So yeah, so you get maybe, let's say 20.
Yeah, so overall it will be less than 100.
All overall less than 100, okay.
Yeah, but even, that is theoretically speaking.
Theoretically, of course.
Ideally one level won't be enough, so if you have to take till you, like, this should go one more level and you should finally end up with taking your entire domain as your one cell. That is where you'll stop eventually.
Eventually, but at every step you're going to get less and less iterations.
Yes. Yeah, for one cell you don't need any iteration, it's a single step, you directly get your answer. Yes. So now coming to it's like the geometric one is, since it is discretizing all of this is quite difficult and it's not straightforward when you have an unstructured mesh. Say something like you can have some mesh like this. Say suppose you want, this is say your L equal to 0. Say on L equal to 1, you might have to say merge some of these cells. So if I merge these two cells, it goes something like this, and I merge these two cells, merge the remaining ones. So here it is at least somewhat little simpler in structured mesh, but now in unstructured meshes, now you have to discretize these cells again, and L equal to 1, and then get the new equations. You have to update all your secondary gradients and all the, again you have to do all of this, and that is a quite like it might take a little more time to do all of that. So you can increase it further, so you can just take a single something like this into 2 more cells, and you can increase the last step is essential to get a 1 cell. But how do you know which one of these ways, like this is not the only way to go to a coastal mesh. You can kind of go in 100 different ways. You do not know beforehand which one of them might work, which one of them might not work, and more often when you have unstructured mesh, you can end up in scenarios where on the coastal mesh you will not be able to solve actually. So you may not satisfy the Scarpero, and then eventually Gauss seidel will not work at all. You might end up in such scenarios also if this is not proper. So the other way that it's developed is in the algebraic way. So here the idea is we do not actually do in the geometry, but then the equations will tend to be grouped in such a way. Say you have your equation as Ax equal to b, so we write it in the matrix form. Or maybe I will just write the initial form. So on the level 0, so you have I minus 1 multiplying with xi minus 1, and then you have the ith one with xi. This is I am writing for the ith cell. So you have I plus 1 to be equal to pi, and say suppose if I write the equation same for, so this is again for a structure, I can write it this way. In an unstructured, you don't have any meaning for IA plus 1, then you have to take care of your adjacency mapping to see what is getting multiplied here. So say suppose we are dealing with structured meshes for now. So you have for the I plus 1, you have I plus 1 I So now if these are my original equations, the error equations are straightforward. So after you do k iterations, so what essentially happens, you replace all these x with your error terms. Sorry. And then your b will be replaced with your residuals. So now when I want to write equations on the I plus 1, so for the I plus 1, or so for the level 1, so I will write b1, say b1i is essentially, if you use the prolongation operator as your addition, simple addition, so it will be r0i plus ri plus 1 for the 0th level. So this is the prolongation operator we discussed previously. So how do I get equation for that? Is just adding these equations. So if this is 1 and 2, I just add these two equations, and then at this stage I will have ei. I should write my equation in terms of ei1 and ei plus 1 for the first level. So how do I relate it? So ei plus 1, so now here we have to fix on our restriction. This is your restriction operator. Here I have to fix my prolongation operator as well. So on the first level, I minus 1 cell should be equal to, or maybe we'll see that a little better. So you can write the equation straightforward here. So on the next level, if I add these two equations, so I'll have I minus 1 0 I minus 1, it's the first term. And then if I group the terms for ei, yeah, I missed something. So this term taken care, and then you have the remaining two terms. And then you have your last term. It's my RHS BA1. I'm just writing directly. So now again we have from the prolongation we know that these are essentially equal to. So if you take your cells, this is my I minus 1, I plus 1 and I plus 2. These are on level 0. So if I did something like I did in the geometry grid, this is your I, and say this is your, so we have even more cells here. This is I minus 2. So if I am merging I and I plus 1 to get my one cell here, and I plus 2, I plus 3 to get I plus 1 cell here, and this is my I minus 1 cell. So if these two are combined to give you this, so if something like this is happening in geometry, so you have EI on level 1 going to EI on level 0, and similarly EI plus 1 on level 0. This also goes the other way. So you have EI minus 1 on level 1. This will be equal to, on level 0, it will be going to I minus 1 and I minus 2. Similarly for I plus 1. So EI plus 1 on level 1 will essentially go to I plus 2 and I plus 3. So if I use these equations and replace them in, say, equation 3, so I will be having A0 I minus 1, E0 I minus 1, actually EI minus 1, 1, plus EI and EI plus 1, both are EI 1 times you have AI I plus 1 and I plus 1 I plus 1, and then the last one EI plus 2 0 is EI plus 1 1. This should be equal to BI1. So this is your AI minus 1 on level 1. So this entire term is AI on level 1, and this is your I plus 1 on level 1. So they are multiplied with I minus 1, I and I plus 1.
So are we increasing diagonal dominance here? Is that what we're doing? Seem
So
to
but
be adding the coefficients, right?
yeah, we are just adding the coefficients because that's what happens on the course. Like that's what we did even in the geometric, right? We are just merging two cells.
That increases the diagonal dominance, isn't it?
It may or may not, right? You cannot always say that it will be more dominant because these are not diagonal elements. So this and these are not diagonal elements. They will be some minus signs with them. It's like if you write in the matrix form, your A and B terms will be negative and you take it to the LHS. So these terms will essentially be negative, and then you might not actually always increase. It's like this.
How do we strengthen the Gauss? Like what is the value that we're adding to kind of
When you actually reduce, when you actually reducing your number of cells, you are making it easier for the information to travel from the boundaries to the current cell.
okay.
So now that you brought it, maybe say suppose you have something like this. So you have Dirichlet on all the boundaries. Some mesh like this, some unstructured mesh. This is say my level 0, and say my level 1 is, okay, maybe you should not take a element like this, but suppose this is my level 1. So you will essentially solve only one equation, so you don't need any iterations also to solve in level 1. So how do you get my AP term here? So you said diagonal dominance is essentially because of your AP term. So if you just see how AP behaves, then we will be able to understand if it is actually increasing the dominance or not. So how will I get the AP term on level 1? So I am essentially merging all these cells 1, 2, 3 and 4. So it should have AP on, say, we won't use any iteration. So AP1 is essentially the AP term for the first cell in the finite domain on or level 0, or maybe I won't use AP, I'll just write A1. So we are writing anyway about for the particular cell. So it will be A1, and then you have plus A2 plus A3 plus A4. So this is essentially your AIA terms, and then you have some cross components, so I plus 1, I plus 1, I and all these terms. So those are essentially your terms corresponding to your phases.
Right.
So it will be essentially minus because you know the way we write the equation, we write it as,
Be on the other side,
yeah, it will be on the other side, so we will have a minus, so that is clear. So then we need to essentially subtract those components. So you have some A12. A12 is essentially the diagonal, the A east or A west term corresponding when you are writing for A1 cell, and similarly you will have the same in your second one as well. So you have to subtract A21 as well. So A21 is essentially the equation you will be writing for the second cell. Similarly you will do for the other ones as well. So you have A23, A32, and for the last one A34 and A43. Now that in each of these cells Scarborough is satisfied, even in the final one the Scarborough should be satisfied. You are not doing anything new here. So Scarborough will be satisfied, but we cannot say that it will be better than the previous one. So what we are doing is very simple. So we have AP0 for say ith cell, it will be something like A east plus A west. So we don't have any source term, so this is my original equation, and for I plus 1 cell it will go as so when I am writing for the next level, for say I am just using a different index, so this I will come from both these terms, so I'll have AP0I minus A east I, similarly AP so this will again will give you the same thing. So you have A east plus A west. Or say previously AP equal to A east plus A west, so this will be A west I, this will be A east I plus 1. So even here these are positive coefficients, so you have your Scarborough being satisfied. So at least only in the equality. Now if you have your other terms, source terms, or because of boundaries, it will satisfy inequality as well. So that is something we discussed previously. When you have Dirichlet, it will always satisfy that. So the method is clear, right? Are there any questions or queries in this?
We got it, yeah.
Yeah. So the next thing is now like initially you asked how many steps we have to do and then how many levels we have to take. Those are the things I cannot comment right before because it changes from problem to problem and all of that stuff. So the next thing that is something called cycles. So what we are doing here is we start at some level, say L equal to 0, and then we take several levels. So L equal to 1, 2, 3. So we have several levels. Say suppose we have something like this. So what we do, we start initially at some level L equal to 0, and then we solve the equation, we get the residuals and go to the next level, and then from there we go to the next level, so on. And once we updated all the residuals, then we go back up. So it goes a straightforward way. So you once come down all the way and then you go up all the way, and then you update your final term. But it is found in the literature that there are other cycles you can do. So cycle is essentially you start from somewhere and then you do all this and come back to the same thing, is what you call a cycle. So there are different shapes, or if you are already, to those of you who are using ANSYS, then if you see the multi-grid option, you will be seeing different options. So there are V cycles, W cycle, F cycle, like different alphabets. So what the shape, what those things indicate is, say suppose you have a W cycle, it is essentially the shape of how you go about it. So when you're actually trying to go from one step to the next step, after reaching the final step, instead of actually coming back to the original one, or say you come back to some intermediate level, instead of going back to the upper one, it is observed that it's a kind of an empirical observation that if you go back to the next level and then you iterate to the next one, it seems to work better, or sometimes it seems to give you faster convergence. So this is an observation. So I cannot give you any theoretical framework that will tell you that it will always be better than the other approaches. So this is also something that you have to do by trial and error. So this is one shape, W shape. Similarly, you can have V shape. V shape is the straightforward one. So you have your different levels. So you start somewhere and then go up all the way back, and then you just do this multiple times till you get your convergence. And then there are F cycles, other cycles that you do. But this is something you have to try. Now if you have completed everything, maybe I'll quickly write the algorithm. So to those of you who want to implement it yourself, it will be quite easy. So the pseudocode goes something like, what are the parameters you will be needing? So you have some solver. So you need your original problem matrix, A matrix. You need some initial guess or solution that will go into the next step, your B0. And N1, N2 are essentially the number of iterations that you want to do. So that is some parameter that user has to specify. First step is always to calculate your residuals. The residual will be something like B0 minus A0 X0. X0 is something you obtain after performing the iterations. Then you compute A1, A2. These are essentially your coefficient matrices on all the levels. Then you perform your cycle depending on whatever shape you have chosen, how many number of cycles you want to take. Then you have to do whatever it takes inside the cycle, or we will write this separately. And then once you perform your cycles, you will update your R value or your residual. And then you just check if your current residual versus the previous one, whatever way, say you can say either this, or you can specify some error, or is less than within some tolerance. Whatever tolerance you specify, if it satisfies that, then you just stop. Otherwise you just keep on doing that. But what do we do here inside the cycle? Say inside the cycle we have some function. we need to perform some iterations of Gauss-Seidel, say n1 iterations on AL for particular level equals PL, and then if you are not on the final, then you take your operators, so you calculate your residual, and then you have to use your prolongation and restriction operators to update your for next cell. So BL plus 1 is calculated. So this is my restriction operator, or in our case, like in the example we discussed, we just use an addition operator. You just take the two cells from which the final cell is formed and then add the residuals from both of these cells. In matrix notation, you can get this matrix RL. So like you can write a matrix, and then like if you're already familiar with it, so any matrix is essentially some operation, some mapping between my one matrix to another matrix. So you can frame this matrix, so you just do the multiplication and then you'll be able to get it. And then you just declare your next one to be 0, and then this is the initial guess that will go into the next one. So you always assume that your initial error is 0, and then you start your Gauss-Seidel iterations. Then you keep doing this. So it's a recursive function. So you again call your fixed cell, fixed cycle. It's the same, all parameters will be same, but you will also specify the level. So say you are evaluating at the L level, so now you will increase this to L plus 1. So this recursion will keep calling the same function till you L reach your L max. If L is L max, the function won't return anything, it will just come out of it. So the recursion will end. So this is the fixed cycle. So after you perform this cycle, you will have your update. So now you can now here you have all your residuals and errors updated. So now you will use them to update your original one. So XL will be updated on XL plus whatever error you have with some operator, that is your prolongation operator. So if I just denote P by prolongation operator, so between L plus 1 to Lth level, some operator, and the error in that level is essentially the solution here. The solution is denoted by XL plus 1, so I am just writing XL plus 1. Now you have this, again you keep doing your original Gauss-Seidel, so it's the second cycle. So once you perform V cycle, again you start from the beginning. So you do that V cycle again and again, so you perform that. And this goes on till your original convergence criteria is satisfied. Now that we can take one example of multigrid and solve, or maybe you can, like you are asking some question, we can actually go to that, and if time permits, we'll go to an example. Now the method is clear. I think you'll be able to do it yourself. Maybe I'll give you the problem, and then we will solve it after discussing the there was one question, right? So we'll go to that question and come back to this problem. I'll just give you the problem now. Simple problem, just to give you an idea of how multigrid works. So you have some cells. Say we'll take a 1D diffusion heat conduction equation. No source, nothing. Maybe just to put some complexity, we will say we have two different materials. So this is some Ka, say 1 watt per meter Kelvin. This is some Kb, different material, say more conductive. Say it is a uniform grid. This is 0.1. You don't have any source terms, SCSP or 0. Now to start with your multigrid, you need to specify your N1 and N2. N1 and N2 are the number of iterations that you need to perform in each level. So I am just taking two levels. So this is first level, and say this is my second level, L equal to 0. This is L equal to 1. And maybe we'll take the last one is a very simple one. So this is L equal to 2. You just combine all of them. So you have two cells here, and this is your single cell. and I need to specify the boundary conditions. So this is 300, say this is 400 Kelvin. So your A and B will usually be, yeah, by now I don't have to solve the equation also, so it should be something like, in your original equation it goes something like gamma delta x by delta y. So in this particular 1D case, so it will be something like k by delta y or delta x. So for the cell 1, what will be my equation? Yeah. So we are in the last class, so you should be able to directly tell the equation without actually solving anything. So you have Ka times T1 minus 300. So it's a boundary cell, so it will be delta x by 2. And then you have, that is on the west part, and on the east part you have T2 minus T1 by delta x 0. So if I just substitute Ka equal to 1, so I'll have delta x is 0.1, so T1 is 30. T1 has a coefficient of 30, and T2 will have delta x is 0.1, so you have a 10, and then you add the remaining terms, so that will come out to be 6000. This is one equation. So now how do I write for cell 2? On level 0,
minus Ka T2 minus T1 upon delta x plus cell 2, right? We're looking at 2.
yes,
So
cell 2.
KB T3 minus T2 upon delta x.
So is it Kb or something else?
Yeah. KB.
So like as we have discussed that this is an interface, right? At an interface you have it's like towards the left it is Ka and towards the right it is Kb. It's two different materials. So
Alright, yeah.
how like there is, we can't just say it is Kb. It should be some function of both Ka and Kb, right?
Right.
So what function is it? So let's say it's K interface. So how is K interface determined?
Be an average of K and KB.
Average of K and Kb, something like this.
Yes.
Yeah, like we have, okay. So there is another possibility. You can take harmonic average as well.
Yes.
So we have discussed why, I think it's already been discussed why harmonic average is better than your arithmetic average, because it gives you physical results, like physically
Right.
meaningful results. So we will stick to harmonic average instead of the arithmetic one. So essentially 2 times by Ka plus Kb. So this will roughly give you some value of around 1.98. So if I just substitute those values, I'll get at the equation here, something like this. And then if you group the coefficients for T1 is your west cell, and for east cell you have, now for cell 3 is not a boundary cell, but it again has an interface on the west boundary. So you have K interface times T3 minus T2 by delta x, and then on the right hand side you have your Kb. You can take Kb because it is in that particular domain,
Yes.
T4 minus T3 by delta x. So just substitute the values. So you will have your T3 is your current cell. The coefficient will come out to be something like this. You have your west cell is second, and your east cell is T4. Now for the last cell is again a boundary cell. So you have a Kb times this term. This particular term will come here with a minus sign, and then you have your boundary. Boundary is 400 Kelvin minus T3 by delta x by 2 is just a half cell. So this gives you, for the last cell, the coefficient is plus, okay, you have 400, okay, 2 kb is almost 100, so you have 8 into 2, 3 plus 2, 5, 8 into 10 power 5. So we just put all the things in one place. So you have AP, A East, North and South. So now I want to write equations for level 1. On level 1 I have two cells, cell 1 and cell 2. Just to keep things clear, I will just write here. So this is my 1, 2, 3, 4 on level 0. This is on level 1. So the equations are straightforward. So how do I get AP on cell 1 in level 1? I know the AP values from the previous one. Maybe I'll write them as well. So it will be easy for you to okay, sorry, it's just a 1-day grid, so we don't even have to write north and south. You can just write P here. I have 4 cells. For cell 1, 30, 10, 6,000. Cell 2, first one is on the west boundary, so you don't have your A west. It's 10. For the second cell, the west one should be the east coefficient. You don't have any p terms. You don't have any p terms. Here you have a p term. For the third cell, AP is 1019.8. West coefficient is 19.8. Should be same as this one. So this should be same. This should be same. Next coefficient is 1000. For the last cell, it's the east boundary, so we don't have east coefficient. The west coefficient should match with this. Okay, maybe now it should be easy for you to tell me how the new values will come. So what will be the AP for first? Okay, maybe first we'll write A east. So for this particular cell, this is the east face. So what will be the east AE value here? A east for cell 1 on level 1 is exactly same as this boundary, right?
Yeah.
So the value for A east here should be equal to the value of A east on the second cell. Yes, so it should be 19.8. So the west one, it is a boundary, so you have 0. We don't write B here because your B is essentially the residual that will come after solving k iteration, so I am not writing B here right now. Now for cell 2, A west should match with this, so this and this should match, so it will be 19.8. It is on the east boundary, so your A0 is 0. So what will be my AP? AP on level 1 for cell 1. Okay, let's not confuse this by writing all this superscript subscript. So how do you get AP on level 1 here? So for this particular cell, to get AP, I need to add APs of 1 and 2 and then subtract the common term. That's what we have been doing. So for cell 1, AP is 30. For cell 2, I have a 29.8, and then I have some phase common between them. This is the east face of cell 1, so I need to subtract a 10, and similarly I need to subtract the west of the other one. So this should give me the value of AP on this particular cell. So how much this comes out to be? So 20 goes off, so you have 39.8. And similarly for cell 2, I need to add APs of 3 and 4. So I have 1019.8 and then 3000. And then I need to subtract the common one. So it's A34. A34 is the east of 3. So east of 3 is 1000. And I need to subtract the west of 4. So west of 4 will also be same. 1000, so 2000. So this will be 2000, 19.8. Is that clear?
Yeah.
Yeah. So now you know these equations. So I told you that I have given in the question is some n1, n2, or you decide on how many number of iterations you need to perform. So once you fix those, you perform certain number of iterations the first one, and then maybe we have to write equations for the last cell, for the last level. Last level is straightforward. So you just have one cell. So you have AP, A East, A West. So what will be my A East and A West for the last? So you have this is level 2, level 1, and this is level 2. So I have 1 and 2 here. This is my 1. So what will be my A East?
0.
A West?
A West.
A West is this. So what will be that?
A West will be 0.
0. Then what will be my AP?
Addition of the 2.
Addition of 2 minus you have to remove these
Minus,
faces.
yeah, 39.8 plus 2019.8 minus 40.
40?
Minus 40.
Approximately 40 minus 19.8.
Yeah, yeah.
So how much this will give you? Okay.
39.8 minus, so that it cancels. So it will come to almost the same 2019.8.
Roughly.
Almost, yeah.
But this is just one equation. So you don't have A East and A West.
Right.
So you can solve it in one step. If you do the iterations, then maybe you will okay, you can actually maybe try later. Now it's already close to 6:30, so maybe we'll take up the ANSYS question. So now you got these coefficients, the next step is actually try to implement and solve them. So that is something that I'm leaving to you, so you can solve them and see if it is actually better than actually solving it the original way versus the multigrid. You can try that yourself. Yeah.
I have a basic question on simple. Can I?
On simple, okay.
Yeah. Can you take that?
Yeah.
Yeah.
So is it on the method, right? Yeah.
Yeah. You know this momentum equation AE star,
Hmm.
right, is equal to sigma A and B U and B star plus say BE plus. I'm just looking at the east face.
Okay.
Let's just take.
So you're using the staggered formulation.
standard formulation
Hmm.
as a discretized momentum equation plus BE plus AE etc.
Hmm.
Now this AE UE star, now AE will have an UE star within it, isn't it?
It's a non-linear. Basically, the equation itself is a non-linear equation.
Now let's say let's take a simple AE is a rho AE
Okay.
UE.
Okay, let me write what you are saying so it will be clear for everyone else. So you have something like this,
Yes.
sigma A and B, U and B plus some, let's say BU, something like this.
UNB star, isn't it?
Okay, star, say star,
Plus,
some
plus
BU, some term, some
yeah.
BU, some additional terms,
some term plus your
pressure term,
Yeah.
say,
Say AE VP star minus.
okay, let's put stars, okay.
Yes. Okay.
So what you're asking is this AE is again,
AE. How do I now? Can you expand AE for me? That would be what? Rho minus rho.
okay, let's say okay, this has lot of terms in it. So let's say A and B, we are trying to expand A and B. A and B will have your Fe terms, right? It will have a combination of Fe and D east. Something like that, right? It has both terms from F and D, and this F will in turn have your rho U delta Y. So how do I get U? That is exactly your question. Is that right?
Yeah. No, I'm talking about the left-hand side.
Yeah, this left-hand coefficients comes from like your A. This is something like your AP term. This is essentially sigma A and B, right? So all this has is some terms coming from this. So if you know this, you will be able to calculate this, right?
Just assuming simple convection.
Oh, no diffusion, only
Not
convection.
forgetting diffusion.
Okay,
Yeah.
so we have simple convection. Okay,
Yes.
then you have your AE coming as some Fe.
AE will have just mass flow terms, isn't it?
Yeah, Fe and F. This F terms.
Yeah, only a west and east face, isn't it?
If it's a 1D problem, west and east face.
1D,
Yes.
1D, yes.
Yes.
Now the U inside that will have a UW and a UE, right?
QEE and UE.
Because
No.
it's,
So you have something like this. Say this is your 1D grid.
yes.
So this is your
I hope
P
it's,
cell.
I hope it's not too basic. I'm sorry. Yeah.
No, it's fine. So this is a cell you are trying to discretize for. So when you are writing your equation, you need the flow rates here and here.
Oh, okay.
So you essentially need U capital E and U capital
I'm
P
sorry.
to get your
Yes.
F, like your convection terms.
Yes, AE, yes.
So now your UE is something you do not know. So this you need to do some approximation. So you will take like your velocities are stored at the phase centers in staggered formulation. So UE you will approximate as U. Say this is east east. So you will approximate in this way. UP will again come from U east and U west by 2. Is that clear?
No, that initial guess is what I'm confused. Now we guess pressures, right?
We guess pressures initially. We guess velocities
Right.
also, right? We need to give guesses for both. Yeah, of course it is lost. That is a different thing. But still we give guesses for both pressure and velocity.
What is the unknown here? I mean, so which is the unknown here that we're trying to solve?
Your UE star. Your velocities are unknowns that you are trying to solve. Yes. These UEs are from your previous iteration. It is like in your nonlinear source terms. It is something like that. You are linearizing your equation.
So UE star we don't know, right? We are
Yes.
using the P star to figure out UE star.
UE star. Yes.
And AE will have the scalar cell.
AE will have this U east, U east, double east, all these things will be there, but these are calculated from your previous iteration values.
Previous iteration.
So that it is not an unknown thing that you have to solve for.
Okay, I got it. Thanks. Yeah.
Yeah. There any other questions?
Sir, my doubt, please consider.
Yeah. If there are no other questions, yeah, we can go with your question. So what you have is something like this. Some constant wall flux.
Sorry to interrupt this.
Yeah, am I audible? I just lost connection.
Yes, sir, audible.
Yeah, someone was saying something.
Yeah, the recording will be available tonight, no? For today's.
Yes.
Okay.
Yeah, so one of you was asking questions, something on answers. So You can go ahead with that. There are no other questions. So this was your problem, right? So you have some pipe flow. Okay.
Yes, sir.
So you have some fully developed flow and through a duct or say a circular duct and with some constant heat flux. You essentially need to find your Nusselt number on the wall, right? So Nusselt number is
Yeah,
essentially given by
Yeah.
something like this. Say if you're defining with respect to your diameter, you know the K of the fluid. The only thing that you need to find is your heat transfer coefficient.
Yeah, hydraulic diameter.
Yeah. So how do you? Yeah, it's a pipe.
Yeah.
So your D is your hydraulic diameter. So
And also I want to find the
plot of what? Yeah, plot of.
plot of Nusselt number versus length.
Basically, you want to calculate Nusselt number as a
Nusselt
function of
number
x.
versus length.
So local Nusselt number versus x. So yeah.
Yeah.
So the question is clear. So basically,
Yes.
your Nusselt number is defined something like.
Variation is like constant for fully.
No. Forget about the final solution. So how do you get it?
The Nusselt number value decreases, and when the flow is fully developed, then the constant Nusselt
So something like this. So this is in your fully developed flow.
4.36.
Yeah. Okay. Now coming to your implementation part. So you need to find. So you know all these things. The only thing that is unknown to you is this heat transfer coefficient, right? Hx. So how do you define your Hx? So you have your wall flux. Yeah, you have your wall flux. Can be written as minus some reference temperature, right? Or you have to fix some reference temperature to get your value of H.
Okay.
So your wall is this again is a function of x, right? You already know this value. So how do you get Hx? So once you run your simulation, you will get the values of TW. Isn't it? It's like from your cell.
At a particular location.
Yeah, you will actually get
the heat transfer coefficient at a particular location.
Yeah, so you have your TW as a function of x. You will get some function. You're constantly flowing, so you'll have some function, and from there you can estimate your Hx. Once you get your Hx, you can actually get this value. So what are the boundary conditions you have specified? So how do you specify your inlet condition? It's like, is it a parabolic profile or you are giving a normal one? It's like uniform one.
Okay.
So what kind of profile are you giving?
Velocity.
Yeah. What is your inlet condition?
Like boundary condition, I considered. Yeah, temperature 293 Kelvin.
No, velocity. What is your inlet velocity? It's like, did you you just
velocity 0.005 meter per
So basically, you are giving an uniform velocity, right? You are not giving the parabolic profile as an input. Yeah. So basically, what I'm asking is, you are specifying some
velocity inlet 0.005
throughout the area, right? Throughout the cross section. So you have specified velocity to be 0.05 throughout the cross section. So yeah, so you haven't specified the parabolic profile, so you have to solve even in the mixing. So your length has to be sufficiently large that it gets fully developed and you get your constant Nusselt number. Okay, fine. So this is clear, right? So how you get your Hx? Once you get your Hx, then you can calculate this. Analysis has this function. It actually has the default functions that calculate Nusselt number on the wall. You can, if you are using ANSYS, maybe you can show it so that we actually thought of, you will share your screen.
Share screen?
Yeah, share your screen.
Yes, sir. Sir, I share screen.
Yes, I can add stop.
side it's visible?
No, I can't see.
Hello,
Yeah, not visible.
it's visible?
No, 1
Okay.
second. Yeah, it's loading. Yeah, visible now.
Outlet.
Yeah, so your velocity outlet is fine. So we already checked these
This is
values.
correct because this is a parabolic and for our laminar.
Okay.
Yeah. But how to calculate the Nusselt number? I think I need this graph.
Yeah, so you go to your ANSYS simulation.
This graph.
Yeah, go to your Fluent.
Yes, sir. This is boundary conditions.
No, I'm asking, can you open your Fluent?
Fluent. Okay, sir. Yes, sir. Yes, sir. Solution part or mesh part?
Solution part. No, like, I think the mesh is already fine. You should have already got it. It's a simple problem, so mesh should be fine with the default one.
Yes.
You are familiar with user-defined functions, right? Are you familiar with the user-defined variables? There are default, but just to give you a flag, we'll see some user-defined ones as well. Hello. Hello. Are you speaking something or did I lose connection again?
I think Deepak sir is on mute.
Okay.
Hello.
Yeah, you are audible
Yes,
now.
sir, we can hear.
Sir, may I audible?
Yeah, you're audible now.
Sir, this is my Fluent.
Yeah, so are you familiar with
Sir,
these functions,
yes.
user-defined functions?
User-defined functions.
So
So I
just
have
go to the
basic
tab.
idea of ANSYS Fluent.
Yeah, it's a basic one. We'll just stick to the basics. You can go to the user-defined one, or there are other options as well. But
User-defined.
yeah, define some named expression, some new expression.
Construct.
No, the named expression, the top below one. Yeah, you can define a function as well.
New.
No, but this won't give you a plot, right? So you just want to see Nusselt number at the end. Okay, we'll see. So you have your outlet location. So you can define functions by your own. So now we have to know your heat transfer coefficient, right? So
Okay.
first thing is your wall temperature. So how do you get your wall temperature? Is just to you can specify the variables here. So you can go to variables. It will give you all these fluxes. So you can actually get the temperature.
Wall fluxes.
Wall flux will give you the wall flux, but the one we discussed, like your case is a constant wall flux, right? So it will be constant anyway, and you know that value already. So just go to temperature and just take, say, total temperature. The problem now is the total temperature will give you the temperature over the domain, but you need the value of Nusselt number at the outlet, right? At the outlet, it is a fully developed one.
Yeah, means Nusselt number is a surface property. So
Yeah, so we need to know the value only on the walls. So
on the wall.
yeah, so now you need to specify your location as well. Okay, it's not how, okay, it's actually a wall averaged one. So did you give a separate, what to say? Yeah, you can select the boundary zones. You have your, okay, you haven't specified the outlet. No, the outlet will be the outlet cross section. It will give you on the cross section.
Yeah, this is cross section.
Yeah, okay, since it is not specified, now you have to actually define a point on the wherever you want to find your Nusselt number. you have to create a new point and then that comes up here. You haven't specified the point, so you have to specify one point. You just cancel this.
Okay.
Go to results.
Results.
Yeah, in that, or you can create a surface. Yeah, create one surface wherever you want to find your
Outlet.
no, not on the outlet. Okay, you don't want on, you want on the wall, right? Yeah, you want on the wall. Say on the wall. You add one point. Close. The tab gives you an option to add a point directly. So click on the points. I think so. I don't know which version you are using. I think it's the latest version. Okay. So close this tab, close this window. On the top there is a results tab, right?
Yes, sir.
Yeah. Now you can create one surface on the left side. Left, even left, the leftmost. Yeah. You create a point.
Create a surface.
Yes. So you create a point. Yeah. Now you give the location of that particular point where you want to find your Nusselt number. It's a global reference frame, right? You know the coordinates.
Actually, attack 0, 0, inlet,
Huh.
and outlet is that coordinate 3.
Yeah, you can specify the coordinates wherever you want. Or for now, we will just stick with whatever is there. Later, you can try changing this. That is actually outside the domain. Okay. So is that point on the surface or not?
Yeah.
It's not created, huh? Maybe try reducing x a little. So just put 0.1 or something now, instead of 0. Yeah. Okay, it's outside the domain. Okay. The idea, maybe I can tell you idea so you can get the points later. Basically, you need to fix one point on the surface. Okay. Then what you do is, once you fix this point, you'll get the temperature from there. But now that this is not working, we can try other way. We just close it. It's anyway not creating the surface. We'll try another way. Yeah.
Sir, how to create a point on this? Actually,
It's a circle, right? It's a circle. So your z, what is the axis of it? Z is the axis, right?
yeah, that is axis.
And your dia is how much?
0.2 meter.
So 0.1 is the radius. So y equal to 0.1 and x equal to minus 0.1 won't be on the circle. So put x equal to 0 is also not working. It's like basically you need to come up with the correct point on the mesh.
So this one, surface.
It's actually not creating. Ideally it should work. I don't know why it's not working. We will try another way. Close this one.
Okay, sir. Please, sir.
Maybe we can try to get directly from the results. You can go to the post analysis, that CFD post. Then there will be an option here to actually get your Nusselt number.
Yeah, this is option.
Density, heat flux. Yeah, you have your surface heat transfer coefficient. Yes. So you can plot this as a function of x.
I got it, but actually result is not.
No, you have to plot this heat transfer coefficient. Oh, you got a linear relation.
Yeah.
So what is the length you have used?
3 meter.
So your entrance length will be around 10, right? No. When is your thermally developed flow? What fluid you are using? Prandtl number is close to 1.
Yeah.
Is it close to 1 or something else?
Yes.
What's the Prandtl number for your case?
Mu Cp over K for water, I think this is
6.9. Okay.
yes.
So you, for thermally developed, you will need a lot more. Okay. Can you plot temperature also once? Just open the expressions.
At,
Yeah.
entire length.
Yeah, as a function of length. Wall temperature as a function of length on the any top surface, say. So temperature is linear.
Increases.
And your heat transfer is constant, right?
It is a wall temperature.
This is wall temperature. Your heat transfer is a constant one. Your
Yeah. Initially it decreases.
No.
Initially decreases like this. This graph.
No. Boundary condition. The boundary condition is constant heat flux. You are constantly adding heat, so your temperature should increase. That is clear. So what is your reference temperature? It might have considered your inlet temperature. Okay. I guess this is something. Okay. No, it's like I was recollecting. So the Nusselt number equal to 4 point something. So what is the reference temperature considered there? So like it keeps on changing with respect to x. So did they consider the inlet temperature? I think they don't consider the inlet temperature.
Sir, at inlet to maintain.
No. So the correlation you are trying to compare with. So you have some reference to compare with, right? So you told Nusselt number is 4 point something.
Actually, sir, my objective is to validate this thing.
Yeah, that is fine. So when wherever you have gotten this, so they would have specified what is the reference temperature with which they have gotten this Nusselt number, right? So basically they wouldn't specify it based on an inlet temperature, but then it will be on something else. So I'm not actually exactly recollecting what the temperature is. Yes, okay. Something to do with if you can get that reference temperature, then it will be a little bit easier. Yes.
Since actually I applied the conservation of energy, that is Q equal to mass flow rate Cp T outlet minus T.
Okay. It should match. Isn't it matching or what?
So 10,000 multiplied by dm. No, this temperature is also not. I calculated from here. Calculator, function calculator. Average.
So what are your residuals? So did you check your residuals?
This is 293. Just
Yeah.
Residuals. Methods. Monitors. So these are the residuals. 10 to power minus 3 for continuity and momentum, and 10 to power minus
No.
6 for
Oh, the criteria are fine. So after the solution is converged, okay, so it converged already, right? 10 power minus 3, 10 power minus 6, so it should be fine.
Yes, sir.
Okay. The Nusselt number you were referring to, right? The reference temperature is not actually your inlet.
Exactly in this problem.
Yeah. So basically, the way you calculated Nusselt number, right? So
How, sir?
one second. So maybe I'll share my screen. One second. Let me share my screen so it will be clear for you.
Okay. I stop this.
Yeah. My screen is visible, right? This is
Yes, sir.
this is exactly the problem you are trying to solve. So you have a pipe, and then you have constant inlet temperature, and then you have a constant heat flux boundary condition, right? So the Nusselt number for this case is defined in a slightly different way. So they are defining it with respect to some mean temperature. So you need to calculate mean temperature, and then you will get your H from there. So Q wall is essentially given by H times T wall minus some mean temperature, T mean, where Tm is defined in this particular way. So you have to get a volume average of your temperature, and then subtract that from. It's not line integral, it's area integral.
Okay.
And then with this you will calculate T wall minus Tm, then you get your heat transfer coefficient, which is a constant.
Line it.
Is that clear?
Sir, how to perform this equation in ANSYS?
Okay. In ANSYS I have not done, but you have your UNT, so it should be straightforward to do area integral. It's an area average or volume average, right?
Area integral.
I'm not sure if the area integral in ANSYS will actually give you this value. The idea is to perform your volume integral, area integral.
Sir, actually, I want to find this graph.
Yeah.
Is it correct, Nusselt? Because initially the value of Nusselt number decreases, and after developed flow, the value is constant, that
Yes.
is equal to 4.36.
Yeah, all of them are correct. The only thing that you have to update approach is to essentially change your the way you define your Nusselt number is something some missing is there. So you have to calculate your wall temperature is already something you get from your simulation. You need to calculate this mean temperature, and then use this relation here, QW, or essentially your wall heat flux is H times TW minus T mean. The only problem now is how you get this T mean. If you can get this T mean, then you can get your heat transfer coefficient. From there you can calculate your Nusselt number, and that will follow the profile you are showing. You got the approach right. The only question now remains is how do you calculate this T mean, right?
Yeah, how to calculate T mean in the ANSYS flow?
That I'm actually not aware of. I'm not sure how do you actually do it.
Actually, I study about this, like T mean and for define del theta over del x equal to 0 for fully developed flow.
Yes. Hmm.
I study about this thing, but how to implement this in ANSYS flow?
Which one? Del T del x equal to 0? So you want to implement the fully developed flow.
Del theta over del x equal to 0 for fully developed.
That comes out naturally, right? Like ANSYS solves your original equations. So that naturally comes out when you give your outlet specification as your far boundary. Like, you don't have to externally specify it, right? If you take sufficient length, then it naturally gets satisfied. You don't have to specify it. Outlet conditions are something we don't specify. We essentially assume that it is a Hyperclear number, or basically, or to say like, the outlet is not actually influencing something at the back. Whatever is flowing, say from left to right, something on the right is not influencing on the left. Everything on the right will get updated only from the left. So you don't have to specify anything on the outlet. If you just specify it as an outlet, then it is taken care
So
of.
first approach, I should
Yeah, the first thing you have to now do is get your mean velocity.
actually
Yeah.
how to mean velocity in ANSYS fluent in post processing.
That I am actually not sure of. So I have not done that previously.
actually-
Yeah.
How to write this expression in ANSYS?
Yeah. That is something that I cannot help you with because I have not done that
If you
before.
know someone who can help me.
I'm not sure. It should be available online.
Sir,
If not, then
sir,
maybe I can connect
if
you
know
offline.
Someone who can help me in ANSYS Fluent from.
Specific to ANSYS
Sir,
Fluent.
actually I searched many times on online and also I could not.
Okay. So, but you are like, as far as this particular problem is concerned, you will be able to write your own code, right? For this particular problem. But you want to solve it only using ANSYS. Like, are you comfortable with implementing your own code,
Yeah,
or
this
you
is-
want to solve it with ANSYS only?
Sir, I know basic idea of ANSYS Fluent like
No, no.
meshing and
Forget about ANSYS
how to
Fluent. So,
plot the results.
no,
But
forget about ANSYS Fluent. That is some framework you have to learn to do it using that. But you can implement your own code, right?
okay.
So one thing you can do is export the results from ANSYS, get all the velocity and temperature profiles.
Implement to do.
No, you export the results from ANSYS, and then you do your own post processing.
Okay.
That would be an easier way, right? Instead of doing it this way. You can just export your velocity and temperature profiles, and then do this operation yourself. Say in whatever language you are familiar with. I don't know if you are familiar with Python, C++, or any language, or even Excel should be fine. This is some basic operation that you have to do. That is one alternate way. You can export results from ANSYS. That is,
Find
I'm
the
sure.
management template, sir.
Yes. The only thing you need to know here is your T as a function of R. That you will know.
Sir,
That you will get.
directly option also available in ANSYS option.
That I am not aware of. So like, I haven't used before, so I cannot comment on that.
We can we use a
Yeah, you're saying something.
sir directly we can in ANSYS directly option of surface heat transfer coefficient like this. I share a screen.
Yeah. There is an option, but I'm not sure what reference temperature it is calculating it with.
Okay.
The way we want is slightly different from. I don't know if what the way the ANSYS has implemented it. So I cannot comment on that.
So 56.678.
What is that? Surface heat transfer coefficient.
Yes, sir.
No, but what is it giving?
Uh, 56.678 multiply 0.2 over में 0.6.
The average surface heat transfer coefficient. It's too high. Okay.
Yes, sir.
No, but no, you are doing this, but we do not know what exactly is the reference temperature that is using to calculate the surface heat transfer coefficient, right?
Yes, sir.
So without that, there is no point in doing this all trial and error. So one way I would suggest for you to check is export these results, do your post processing yourself.
Sir, if you know someone who can use the ANSYS and expert of ANSYS Fluent, like find the result number.
I'm not aware of anyone like that. Like we usually write our own codes. So, like post processing is something you just use the simulation.
Okay.
ANSYS only for the simulation part. Post processing is something we write our own codes for. So I'm not aware of anyone. I cannot help you on that. Sorry for that. If you have any conceptual related ones, then maybe I can help you on that.
Okay, sir.
Yeah, thank you. Yeah, we're almost. Yeah, it's almost 7 o'clock.
Okay, thank you so much, sir.
Yeah, it's almost 7 o'clock. Thank you all for joining. And yeah, this is the last session for this course.
Sir, what is your mail ID?
What is your?
Sir, what is your mail ID?
It's the one shown here, right? Okay, isn't it showing my mail ID?
Sir, mail ID, mail ID.
Yeah, the one that is shown, right? me22d400 @smail.iitm.ac.in. You have to add. Okay, one second. I'll just post
Sir,
it.
please type.
Yeah, I'm just posting. Yeah, if there are no questions, then we can conclude the session for today. Yeah.
Sir, one doubt. For
Yeah.
exams, it will be a multiple choice, right? Same like assignment type.
Okay.
Will the question will be similar to that assignment type, or should we focus on anything important?
Okay. I cannot actually comment on that. I request you to post that question in the discussion forum, so you'll get the reply from the correct person.
Okay, sir.
Okay. Okay, then we'll conclude. Thank you all for joining. Okay, have something?
Okay, thank you, sir.
Yeah, thank you all. All the best for your exam, for whoever
Okay,
is
thank you
writing.
so much, sir.
Yeah.